So, Padma ma'am, you already started the recording, right?
Yes, sir. It will be
Very nice.
available.
Yeah, I was trying to
Yeah, I
do the
have
same.
started.
So,
I'll share it. It
okay,
will be available to the participants. And also I'll share it with you, sir.
great. So I need not to worry about that. All right, got it. Okay. So I've been told that there is a lecture going on. So we just need to wait for 2, 3 minutes more. So I'll do so.
Yes, sir. Can we start? Uh, okay, sir. Kavita ma'am has joined. I think we can start the session. We are ready now. So we invite on behalf of VIT, we invite Mr. Pavan, uh, who is the CEO and who is going to give the talk on superscalar architectures today. So the students who are here are current second year students doing their BTech in computer science, and they have the course on computer architecture and organization. So we invite you, sir, once again for the talk. You can please now start. Thank you, students. Also.
Thank you very much. And I hope my voice is clear and loud enough for you to listen. Thank you so much, the entire VIT faculty staff for inviting me to share the experience and knowledge with the student for the scalar architecture. So for that, I like to request for sharing my screen. It
Yeah.
looks like only meeting presenter can present and share. You may have to give me that
Uh,
right, actually.
um, sir, is it requested by you? Because I'm not able to see the
Um,
screen.
no, so I can, yeah, it's when I'm hovering on the share button, it
Okay.
says only meeting organizer and presenters can share. Um, so,
Okay. Okay. No, because why I'm asking is it's not showing any option for me to uh, permit you here. One second.
okay, might be, let me maybe join again, if that helps.
Okay, sir. I'll try.
Okay, I'm joining in a second. Okay.
Sir, I have now given the option. See whether you're able to access it. It's not yet.
Can you hear me?
Yes. Yes, sir. I'm able to hear you.
Yeah,
And
I can share. Give me 1 second. Sorry for this trouble.
no, no, it was on my side. I have now changed the option.
Got it. Okay. All right. So let's get started, guys. And again, welcome you all. And let me see if I can turn on my camera so that we can focus on the slide. Um, all right, so can somebody confirm, or Padma ma'am, if you can confirm you see a slide, scalar,
We are
super
able to
scalar.
see, sir.
All right.
Superscalar computer.
Okay. All right. So my name is Pavan Agrawal, guys, and I am heading organization Bits Atom Technologies and working on couple of AI projects, some of the legacy softwares. We work on the computer applications. The reason I'm telling you this is because we face low latency requirement in time to time when we are implementing our solution for the real world. So to start with that, the superscalar computer architecture, it's a very fancy word. We'll, fraction it out and try to understand what it is. But if you see a subtitle here, it's advancing instruction level parallelism. So there is an instruction life cycle and there is a parallelism. If we'll combine both and add a little more complexity, that goes to super scalar computer architecture. So let's talk about it. Um, So let me just add the agenda here. So we'll talk about the superscalar architecture. What does it mean when it got invented? The basic of pipeline architecture we'll talk about. We'll also talk about some of the key features of the processor that caters this capability. And then we'll talk about some of the advantages and challenges. uh, then we'll talk about the modern CPU that those are using or complementing um, the multi-core processor with the superscalar architecture and why they are being used. Then we'll talk about the future trends and best fits in the current market. So, all right. So it got invented. So superscalar architecture, we call it SSA as well, got invented back in 1987. It executes multiple independent instruction in parallel. So like I talked about in the first slide, that there are instruction life cycle, and those instruction life cycle are going to execute in parallel. And we'll again decrypt it, this complex thing, a little later in the slides, right? And so the common instructions like arithmetic, your chain of small instruction that cannot afford high latency or communication gap, that is being used, and that leverage the superscalar architecture, um, and they initiate simultaneously and execute independently. These This architecture is applicable to RISC and CISC, where RISC stands for reduced instruction cycle, and CISC is for the complex one. So let us talk about what is the basic of instruction pipelining. There are four stages to, the five stages to that. One is the fetch, then decode, then execute, then memory access, meaning writing back to that and explain it, then write back to the register or memory. So fetch is where the processor fetches multiple instructions from memory in a single clock cycle. Decode is where the first instruction from the stage one gets into further decoded machine level operations, right? So let's say you are saying 2 plus 2. how this 2 plus 2 machine is going to understand. It will decode and then tokenize it, and then actually does the execution part of it, because your 2 plus 2, you all understand, the computer does not understand it. So instructions are dispatched to multiple functional units that we call it maybe a thematic logic unit, and or maybe FPU, floating point unit, and so on. So they get executed on this stage. Then on the green one, memory access, where the executed instructions are then loaded and then stored in operation to access memory and cache. Once everything is done, the result, once we get the result, it gets right back to the registers or memory on the very low level. So this is what the instruction pipelining is, right? Then here, little, no, I tried to create it, but the diagram is not so pleasant, but let us understand the basics of it. So what is superscalar processor? So we just talked about, 5 stages of instruction pipeline. So if you see, oops, sorry, yeah, if you see here, um, if we consider the parallel line here as a one cycle, then if you see, when the processor is fetching the instruction one, no other no other things are happening, right, in this stage. And then on the next stage, when the instruction 2 is coming, then only it can take instruction 1. So if you see here, the
See, please mute yourself, participants. Please mute yourself.
uh,
Sorry, sir.
thank you, no problem. So if you see here, we are seeing a little latency. So where is the latency I like to highlight? So while it is executing the instruction 1, there is other instruction which is waiting for this I1 on the first column to be waiting, right? However, on the superscalar architecture, when instruction 1 is getting fetched, instruction 2 is that is decode is being happening on the other side in parallel. On the same time, when it goes to the next stage, the third and fourth instruction are getting fetched, right? So if you see that when it is going to decode mode, correct, instruction 3 and 4 are coming to fetch mode. So this creates a parallelism to the instruction pipeline. So if you go back here, this is the instruction pipeline, and how we are trying to create a parallelism here. We are not letting the other processor to keep waiting. We are rather doing a parallelism that, okay, while my processor is decoding, I can have my other two jobs, that is I3 and I4, to be getting fetched and doing other activity. And these goes on, uh, and so on. Like this is a very simplest way of this chart, right? But the real processor graph is very complex, that we can call it as like hyper threading, where the processing is happening. But yes, at the base level, the concept is we need to avoid the latency. That latency should be low between the instructions. So there are key features to it. Let me try to explain you. So there are multiple functional units that we already talked about it. Instruction dispatch and issue. So there are stages where instructions are getting dispatched and they are issued to the execution in units, right? Then the other important aspect of it is like out of order execution. How it maintains out of order, again, this is very within the processor thing, but let me try to attempt to explain you. So in this instruction, if any instruction are getting out of order, that means maybe you are thinking that this instruction need to be executed in given timestamp, and that timestamp is getting lapsed, then again it will get reissued within the same cycle and does the in thread within thread execution, right? Then renaming. So register renaming is very interesting concept where we reduce the conflict by same register during out of order. So let's say your instructions is stored in a given register, and you already registered that in your instruction pipeline. So what you do, what the processor does, it renames the register in order to renew the instruction and again requeue that in the instruction pipeline, right? So this is where out of order execution, this is a very good concept to understand. So I like you to I'll encourage you to understand this, maybe go in more details and maybe other sources, and you can reach out to me anytime in our email, that is info@vitsatom.com, and we'll definitely help you out. Then the next one is again, what is the advantage, how this entire thing works. So when your instructions are coming and they first come to the memory, right? Then what you do, you take those into fetch unit, you fetch the instruction, then you decode it, then you do multiple instructions and give it to execution unit. So this is, I tried to show you a parallelism. And once the execution unit completes its task, it goes to a register file where you actually write back. That goes to the fifth stage of instruction pipeline. Um, So here, the challenges, what are the challenges? So for now, we already talked about out of order issue, right? How it, reissue the instruction by renaming the register. So there are multiple functional units that when there are multiple functional units, then it creates multiple functional units, constitutes to more hardware uses, right? More hardware uses tends to increase the power consumption and heat. When you increase your resistor, your capacitor, of course, there will be heat generated. So that's kind of a challenges in superscalar design. Moving on, what are the modern CPUs? So the modern CPUs that we use currently, those are Intel Core 9, where multiple execution units are there with hyperthreading. We talked about it in the earlier slide. That's a little illustration, like very hyperthreading might be very fancy word, but you can see that we get multiple instruction, but the process takes single threaded. But hyperthreading is where we take multiple instruction and output multiple instructions. Like you must have seen read like dual core, quad core, that kind of processor. That is for the multi-threading and impose the parallelism. AMD also have its Reason processor. That's a example of simultaneous multi-threading. Uh, then future trends, multi-core versus superscalar. So one would think that, okay, if I have superscalar architecture or the processor, then why would I need multi-core? So there are limitation to superscalar, and we talked about how it can, be creating a more complex hardware. At the same time, it generates a lot of heat. So you must have noticed, I don't know if you guys have, ran the AI models locally.
But if you run AI model locally, no matter how big your configuration is, your computer will be, burning after maybe 2, 3 hours. We do day to day. So we have added the GPU, graphical processing unit, and the GPU is actually leveraging the superscalar thing. So it generates the heat of today also, but again, the instructions, the language training, the training model that we are training day to day is little faster, and we'll talk about it. Just trying to tell you that how it can complement the multi-core design. So no processor is coming in the market as pure superscalar. They are in complement with multi-core. So you see multi-core processor and the superscalar architecture gets implemented for a special and very targeted purpose, then we'll talk about it. Then further AI and machine learning, we talked about it. CPUs optimized for vector and matrix operations. That is not the kind of scope of this session, but I would maybe later on we'll talk about how we can train model and the AI and machine learning and what is vector and matrix operation, and in reality on real time how we can see those operations happening and getting consuming the memory and the processing units. Beyond superscalar, what is going on in the market and what is the future? You can talk about the quantum computing. You must have heard about this word. Many countries are working on it. We haven't touched it. It is like beyond our capability for now. But yes, we would like to get our hands dirty in the near future. Branch prediction, then s- speculative execution, stuff word, but I we don't work on this. But yes, quantum computing is something that is more than the superscalar and multi-core in short. All right, moving on. It is very essential for anyone to understand what is multi-core um, versus superscalar architecture. Excuse me for this writing mistake. Sorry. Let's see. It's all in rush. Okay. So coming back here, um, so let us understand it because the subsequent slides are very much related. If you'll understand this slide, then the later slides will be easy to understand. You'll be able to correlate that, okay, why I'm reading, why we are studying superscalar. So far we talked about it produces heat. It, it cannot uh, process the instruction as many instructions as multi-core does, then why superscalar architecture and what is the use of it? So let us talk with the help of this small table, and then we'll talk about the use cases. Those are happening in the real world. So the aspect here is that parallelism type. It's a thread level parallelism. Here it is an instruction level parallelism. So there is a difference that a single thread will be used and instructions are divided. Here, it creates a thread level parallelism that, okay, one thread is dedicated to one task, and then the other task will be dedicated to other thread in multi-core. That means when I want to give instruction, a single instruction to a given thread, then two thread needs to be in sync in order to produce me a result fast. But in reality, I'm talking about multi-core. In reality, there is a latency when two threads are talking and maybe joining in order to produce us the right result. So here, superscalar architecture where we cannot afford a lot of latency means, the time gap between two instructions or two processes to join and give us the final result. Then we talk when we consider superscalar architecture. And this is why I was referring that superscalar architecture, complements multi-core, right? To um, get some of the instructions, some of the execution that cannot afford a high latency.
Then the next one is the execution units. Of course, we know it is multi-core and multiple cores are there, and each of which have its own pipeline. So the instruction will go and go to a single core, gets its own pipeline. Then other instruction that we send to other pipeline, then they get joined, and the time gap I'm trying to refer to the latency here. The single core multiple instruction units, we already talked about it. The focus area is multitasking and parallelizable workload. So the workload which can afford parallelism, we put that into multi-core processing. But the workload that cannot afford parallelism, that means a latency, then we put them into superscalar architecture. We in day-to-day life, you don't feel which architecture is being chose by within your computer, but it is happening when you are seeing the YouTube video, then that execution where there's not a single latency you can afford, then it is some way is utilizing superscalar architecture. At the same time, when you are writing, you're seeing videos and or maybe learning something and writing your code, then multi-core is also happening because there are two separate threads are going on. Like I discussed, hardware complexity, of course, it is going to be moderate, but moderate is also very complex. But in superscalar, it is going to be super complex, and that tends to generating a lot of heat. And generating a lot of heat, let me talk a little bit about how data centers are being managed. So like Amazon, Azure, and Google are managing their data center. So one of the most complex issue that they are trying to solve is how can we reduce the heat generated by these data centers? Because imagine that you have maybe 100 Xeon processors in a rack, and two processors are generating the heat. Then rest two processors will be get influenced and generate more heat, right? And will be slow because of that. And when the computer is slow, then the processor will try to execute it fast. So that's a kind of race condition that happens, right? And that race condition tends to a cascading effect and may create very much heat, and that tends to low performance data centers. So these companies are working very aggressively in order to make their data centers performing, and that tends to the virtual machines that we are seeing right nowadays are very much performant. So there is a lot of complexity is being added. So that's why I was referring that superscalar architecture, the problem, the heat that is it is getting generating is creating a problem, and this is how we combine multi-core and superscalar in order to produce the best result out of it. Then software dependencies, of course, it requires multi-threaded software. So software that can leverage multi-threaded will be the best suited for multi-core. Otherwise, if your software cannot leverage, so let's say you have written a program that is actually leveraging the multi-threaded mechanism. Maybe in Java, you must have written multi-threaded threading. So that threading, when you're writing, it actually talking to the processor and checking that, okay, I got three thread. Do you have three core processors for me? So, processor says through the JVM, the Java virtual machine, that yeah, I have it. Just send me. So it sends the instruction that gets executed in parallel, and you get the result. Here, this is not a big problem. So it is like, available to most of the softwares. Scalability. Here, the scalability is it scales by adding more cores that we can say, call it like, okay, it's super scalable. But in superscalar, it is not limited. I mean, it is limited to instruction level stream dependencies. Like, okay, I'm on the decoding phase, right? if you're decoding phase, you really cannot execute it, right? So that creates a limitation on that. But what we are getting out of it, low latency. There is no really a latency between two instructions to be executed in superscalar the way it is designed. Uh, the application where we would apply this is multitasking, parallel processing, and however, in Superscalar, it is high performant single thread task, and we'll talk about what those are. Uh, we'll talk about some of the best fit where the Superscalar, since this session is for Superscalar, so I left behind the multi-core. Let's only talk about superscalar so that we understand that what we are studying is being really used in real life, right? So use case is application that rely heavily on sequential processing and cannot easily be split into multiple threads because it is not multi-core. It complements multi-core, right? So the legacy software designed for single-threaded execution, believe it or not, um, we have been working on a couple of maintenance projects. Those got initiated back in 1987 or 89. And those were based on very outdated software, and we had to maintain that in AWS virtual machine. AWS does not have that old software or old course. So we have seen that even if we'll put Xeon processor to these softwares, you will not get that kind of fast because these softwares were not designed to leverage multi-threaded or multi-core processor. Okay. I mean, we have, and this is one of the very basic of working on the performance optimization. Sometimes we only talk about in software, we talk about, okay, did I write my for loop right? Is it having n plus one query? Is it having, blah, blah, blah. But of course, if you go ahead and go to little deeper, how it is leveraging the hardware, the entire architecture, then you'll get to see that multi-threaded, and if it is leveraging multi-threaded properly, then your software is bound to be performant. Application layer, of course, we can solve, but at times your application layer is perfectly written, but really your behind the scene, the underlying language is not supporting. Sorry, then you'll not be able to create a super performant application. So let me take a chance to explain you how it is impacting. So in Java, we know that Java is super multi-threading application, language, and its multi-threading capability is, I think, best out of many great, languages. In our one of the um, project that was on Ruby on Rails. I don't know if you guys are aware what is Ruby on Rails. So Ruby is a language, Rails is a MVC, framework. So one of our client came and talked about that. Okay, we are seeing a performance issue, and even we are increasing the. Just give me 1 second. Let me take water. Sorry. So they came back and said that one of our server, when we restart the server, what happens that uh, it gradually eats the memory. That means it acquires the memory, and that memory does not get back to the maybe garbage collector. Some
Participants, please mute yourself. Are you able to see?
Oh, yeah, I was talking in mute. I'm sorry. I got muted. I don't know how. So, what I was trying, yeah, so I was trying to give you an example of the baseline. So we, of course, you will get the theory of the superscalar architecture, multi-core in books and wherever. But I'm coming from industry, so I'll talk about how it impacts us when a real-time problem gets to us and we solve it. So client came and talked about that, okay, our application over the time of 10 to 15 days, it eats almost all of memory and processing units, and our processor, our server is not responding. So somehow this problem ever existed for 7 years down the line with them, and it was one of the pain that they have to go to on Sunday night, a Saturday night, or then the weekend starts, go and restart the server so that the memory and processing unit gets reset. When this project came to us, we went ahead, analyze, and we also took a lot of time, like 10, 15 days on analysis itself. Then we went ahead and thought about some theory that, okay, why it could be possible. Then we came to know that unlike Java, Ruby does not leverage multi-threading a lot. That means it itself, if you'll create a big server, it cannot leverage all of its servers multi-threading, multi-core very efficiently. What we did, we create a very small servers and given a very small number of threads to each server. So for example, for instance, one server was taking maybe 50 thread that we aligned initial, before we our performance team. Then what we did, we created 25 servers, small servers with the same cost, and given only two threads for each server, and it solved the problem. Not only that, we found that when it was 50 thread, only 5 threads were being used, and we could not find you know, it had lasted for years. So we reduced the servers to 10 small servers. Still, we got the best results. So almost 5 times cost got less, no no kind of slowness. So what I'm trying to make my point here to you students is that when you're learning these things, this is really impacting the world. And that's why these things are in your curriculum. Coming back to here, I wanted to give you some, real life issues, problems that can be solved when you understand the threading, right? So the real-time systems where predictability and low latency executions are crucial, weather forecasting, your stock market where your continuous streaming is required, not a single second stocks and ups and down you can afford. There, superscalar architecture comes to the play. The other best fit here is you know uh, latency sensitive task. I've been talking, if you heard the hashtag in this entire session was to task those cannot afford low latency or high latency. I'm sorry, low latency, of course, is always good. Task where low latency processing of each operation is crucial, as superscalar architecture reduces execution time for individual threads that we already talked and understood. So the example of it is audio and video encoding and decoding. Of course, we talked about YouTube, where you even cannot afford to. So your video is coming in the form of stream, then your player is taking your YouTube player is taking the computer hardware processor to decode it to show you. Right? So you cannot afford to have that kind of latency there. Otherwise, your video is maybe cluttered, or maybe a lot of buffering, or maybe it's flickering as well. The other example is real-time gaming engines for physics simulation, for AI decision making.
AI is a little, a time-taking thing. So of course, one day we'll definitely talk about it. But yes, real-time gaming and not gaming is always that Mario and other superstars. Gamification is where you are adding instruction that somebody is reading very, very real time, right? So that is gaming. Don't even consider gaming is the game that we plain computer. Gamification is where you are engaging someone, it may be human being or the other machine, for your instruction to be read in real time. um, Database queries requiring fast execution of a single threaded operation. Believe me, we have never used it. It is like being used might be in data decisions or little more complex kind of projects. We haven't taken this into consideration, but I took this here just to make you aware what's going on. The other best fit for the performance critical embedded system, the software where space, power efficiency, and the real-time performance are crucial. Space, I do not have a much idea, so I don't want to talk about it. Power efficiency and the real-time performance. So um, I don't know if you're aware, but our grid is nowadays being governed by embedded system where it distributes the power to the cities. So main grid is there. The uh, smaller cities are be getting distributed. So it reads the instruction that okay, if the power is consumed less, then it cuts the little power and distributes to the cities where it is needed. But when it cuts and when it is redistributing, I'm telling you very high level, having a little bit knowledge of it, let me tell you. But you should know where the real life application is being used. So that's why I'm telling you. So when uh, power is being read, a power consumption is being read, there must be a device that is reading and telling the instruction to these embedded system. This is where the microcontroller and IoT devices comes to the play. Maybe you can go ahead and check how the grid system is being evolved in India to use these embedded system to distribute the load and whatnot. So and where there you cannot afford any delay because your light will be goes on and off. Maybe voltage will go on and off. Your equipment will get distracted in a certain way. Signal processing, yeah, of course, very good use. Radar, sonar, and medical imaging system where you cannot afford a single microsecond kind of delay. Your radar, your aircraft is coming. If your radar is not, having a high performant, low latency, then you tend to have many issues. Low power processor for mobile and edge computing. Edge computing, I'll encourage you to go through. I don't, have good, material for now, but low processor for mobile where, so let's say you are switching from one screen to another screen. So if you have noticed, some of the mobile takes little time in switching them, and then it some of the mobile is having very seamless, and that's how they are leveraging the superscalar in a better way. That's how it goes to the real life. Anything, any place where you don't want to see latency, and you really don't see latency, you always thanks to superscalar architecture invention. um, Again, I tried not to put AI stuff because it takes the discussion to a certain different dimensions, but it's still the world is revolving around AI. So wanted to talk a little bit where in what part of the AI the superscalar architecture is getting leveraged. So use case would be a certain AI ML task that involve smaller model or low latency inference. So in some of the, so let's say you are sending instruction to chat GPT, it creates your instruction to token by token and generates a small score token by token generation where you know and then it sends to the NLP, that is network natural language processing. There actually superscalar architecture comes to the play, running a decision trees where one node cannot wait for another node to get executed. So there you need that kind of uh, processor to come to the play. And one thing that I like to discuss, and I was going through and I was preparing for you guys, that everywhere you see superscalar architecture ensures low latency, but it also is the fact that the huge complex operation it cannot do alone. It will be doing with the companion of multi-cores. That's why it is written like low latency real-time inference on embedded system. So always think this as the companion of multi-core in order to perform end-to-end results. And thank you. I think that's it. I would encourage everybody to write me if you have question. Um, the email is info@bitsatom.com. You can go to our website www.bitsatom.com. And once again, thank you so much, entire VIT, Kavita ma'am, and other faculty staff to invite me in the session. And also, if you have any feedback or any more lectures you need from us or the real-time processing you want to see, please let Kavita ma'am know and we'll coordinate and we'll come back to explain that to you as well.
Thank you,
Over to
Pawan sir,
you.
for your session.
Yeah. All right. Thank you so much, everybody. Take care and bye-bye.
Thank you, sir. Thank you.
Thank you. Thank you.
Thank you, sir.
Yeah, thank you all for joining.
Thank you, students, for joining the session. Thank you. We'll share the PPT in a WhatsApp group.